So I want to start by saying after our last class, someone came up and said, what do I do? How do I find the parameterization of a curve? And there's a couple of things that happen. One, they'll just explicitly give it to you. And then it's like, oh, it's easy. It's that one right there. It's whatever you see in front of you on the paper. If they don't give you a function, but they give you a picture, then you say, well, okay, is it a really easy picture like a straight line? Well, that we can handle. We'll talk about that in a second. The crazier it gets, the better the news for you. So if they ask you to find the integral along a curve, and it's this wacky, outlandish curve, we've got great news for you. And that's coming up. That's what we're building up to today. But other than that, the three things you might see are a portion of a circle. And I talked about here being centered at the origin. You can, of course, move it to be centered at any place, h comma k. If you want to move it, just add in h in the x direction, add in k in the y direction. So for circles, always use sines and cosines. Why sines and cosines? Well, because those have really clean derivatives, and that makes your ds term very easy to work with. So that's how you handle anything that's a circle. If it's a straight line segment, you say, oh, we learned how to parameterize lines, the parametric form for lines. And it turns out it's really very clean. And so if you think back to the first part of the course, you said, okay, you have 2 points. You find the vector between the 2 points. You choose A, B as your start, C, D as your end. Then your parameterization is you put your initial point as your point, plus the pieces of your vector times t, and you let time go from 0 to 1. This works in any dimension. So if you're asked to find the integral along a curve, for anything that's a line segment, we can find lines. We know how to do that. And then they might say, well, I'm not giving it to you as a parameterized curve, but it's y equals f of x, where x runs from a to b. Say, okay, just rephrase it. In that case, x of t is t, and y of t is f of t, and time runs from a to b. If you can do this, you can handle any question we're going to ask you, at least for the portion of the question of what's the parameterized curve. So these are the three things you need to be able to do. Okay, any questions on finding that parametric curve? All right. We finished at the end of last time. We were talking there's two kinds of integrals for line integrals. There's the integral f of xy ds, the one where orientation doesn't matter, and where you get an unpleasant square root. And then we said, oh, there's another one which has a couple of different ways it gets written. Sometimes it's written as f dot t ds, sometimes it's written f dot dr, sometimes it's written m dx plus n dy. But that one has two square root terms which cancel out, meaning no more square root terms. Yay us. Woohoo! But the other thing is that's the one where orientation matters. So we're going to pick up at that point. So as a reminder, if you're given a parameterized curve, time runs from a to b, and you're asked to find the integral along the curve, m dx plus n dy, what do? Put everything in terms of t. That's how we do line integrals. Everything gets phrased in terms of t. So x and y become x of t and y of t. dx becomes x prime of t. Our integral along a curve goes from the integral a to b. So let's try this out. So find the integral along the curve xy squared dx plus xy squared dy, where we're going from 0, 0 to 2, 2, and the picture, hopefully it makes it clear, is meant to be a straight line. All right. Well, what do we need to do? So it's an integral along a curve. We need to put everything in terms of the parameterization of the curve, which is like cool, except what don't we have? We don't have the parameterization or parameterization. Or it's a very long word. I wish we had a shorter way to say this. The make it t thingy. But that's okay. There's a couple ways to do this. Do you recognize this as a piece of a bigger line? What line would this be? Y equals x. So you can say, if we think of this as y equals x, a parameterization, not the only one, but a really simple one, would be t comma t, x equals y, t equals y, for 0 less than or equal to t less than or equal to 2. That will start at 0, 0, it will end at 2, 2, and it moves along the line in the right direction. Okay, so what do? Well, everything gets phrased in terms of t. So the integral, now we're going to replace the c using the bounds, 0 to 2. What will x become? T. What will y become? T. So t squared dx, x prime, dt. So for right now, we'll just put a 1, we'll put a dt on the end. So it's t times t squared plus x, 1, y squared, x is t, y squared, t squared, dy, 1. So this becomes the integral 0 to 2 of 2t cubed. What's the integral of 2t cubed?
1/2 t to the 4th.
1/2 t to the 4th, because you would add 1 to your exponent, making it a 4, and divide by 4. 2 divided by 4 is a half. Plug in from 0 to 2. Plug in 0, you get 0. If you plug in 2, what do you get? You get 2 to the 4th is 16 times a half makes it 8. So these are actually not bad integrals, right? You just plug everything in terms of t, compute it out, life is good. Okay, now, let's do it a second time. Notice we're integrating the same thing, xy squared dx plus xy squared dy. What has changed? The curve. And notice we still have the same start and stop, it's just how we get between the begin and the end. Now, you might say, you're in trouble, Steve. That's not a straight line. There's a right turn in there, and that's not a circle. It's not a parameterization. What are you going to do? Well, we have fancy technology called split it into two problems. So let's think of it as two parts. We'll move first horizontally, and then second vertically. So I can say, look, if I want to find the total, I can just say, let's see what happens on C1, and let's see what happens on C2. We put the two together, life is good. So let's talk about C1. We're only moving horizontally. What do we look like? Can you think of a nice parameterization that only moves horizontally, starts at 0, 0, ends at 2, 0? T comma 0. Where does t go from? 0 to 2. All right. How about for C2? We're only moving vertically. What do we look like?
0, t.
2 comma t, right? Because we're at 2 comma t. And then where does t go from? 0 to 2. They might say, well, wait a second. Hold on. These don't seem compatible. Well, they're different curves. We don't have to be compatible with each other. We're saying, look, split into two problems. Each one is its own problem. All right. So we begin. Let's start with C1. All right, we're going to integrate from 0 to 2, because we're using our 0 to 2. What is x? T. What is y? 0 squared, but that'll accept 0. dx? You're probably like, Steve, it doesn't matter. There's a 0. Why do you keep going? Plus x t y, still 0 squared, dy 0 dt. Well, what does that turn out to be? Can you do that one in your head? I heard 1, I heard 2. It's a little bit less than 1 and less than 2. What does that equal? 0. And if you add up 0, between 0 and 2, what do you get? 0. The integral of 0 is 0. If you're adding up a bunch of zeros, you get 0. Okay. Cool. We learned something new today. All right. C2. Well, hopefully this gives us something. Well, bounds are still 0 to 2, but it's different parameterization. So hopefully something new happens. What is x? 2. Y squared? T squared. dx? 0, because derivative of 2 is 0. Plus x, 2. Y squared? Still t squared. dy? 1. Okay. So we'll simplify this a little bit. The piece with the 0 goes away. So this is the integral of 2t squared dt. What is the integral of 2t squared dt? 2/3 t cubed. Plug in 0 to 2. We get 2/3 times 8, 16 over 3. Now, why did we do this? Well, to practice, but also it's the same things we're integrating. The curves have the same starts. They have the same ends. But what do you notice about these two numbers? They are not the same. Disappointing. Now you might say, why is it disappointing? Well, we'd like them to be the same because that feels like what calculus says. You know, somehow, if you think back to the good old Calc 1 days, our fundamental theorem of calculus says, oh, if you're integrating a function on an interval, you find the quote-unquote antiderivative, and then you just evaluate that at the end point. So it's like only the end should matter, not the middle. So the fact that it matters which curve you take is not cool. But maybe it's because we're integrating the wrong kind of a function. And that's what we're going to talk about. That lets us segue into today. All right, so with that out of the way, a quick thought for the day from Albert Einstein. Any fool can know, the point is to understand. This gets back to, what does it mean to have knowledge? Some people are like, oh, it's an on-off switching. You know something, you don't know something. But knowledge, it's a spectrum, if you will. You can go from a complete ignorance of something to a very in-depth working knowledge of something. And the goal here is to say, look, it's not enough just to know something. You have to go further. You want to get to mastery. You want to get to the point where you can understand. You want to know why things work, because then you can make them work. All right, so our goals for today, we're going to do the fundamental theorem for line integrals. And it says, hey, that rant Steve was going on, there are nice functions in the sense that there are nice integrals where it doesn't matter the curve that you take. And that there is, in some sense, an antiderivative. Now, what are the nice functions? Well, they're the ones which are gradients. Or you might say they're the ones which have potential. So we talked about the idea of a potential function for a conservative vector field, which is a gradient. So integrating gradients is nice. The only thing you have to do, find the potential function and evaluate what happens at the end minus the start. So we have to talk about how do you find that potential function? And then there's another strategy, BYOC. Bring your own curve. If you don't like the curve, bring your own curve. Find a better curve. And this is a nice strategy. I will say that this shows up in our formula sheet. And we're sort of at the point where we're going to sort of cascade through the last 4, give or take, over the next few weeks. I like to call this part of the formula sheet sort of like, hey, fundamental theorem of calculus for Calc 3. And we're going to talk about 4 variations. So today is our first one. All right. So we begin. And the good news is that the fundamental theorem of line integrals is very quick to prove because we have all the pieces in place. We start with a little reminder. We did the chain rule. So we say, all right, we have that a function, f, is a function of x and y. So when I write f here, I say f is f of xy. And more particularly, x and y are themselves functions of t. So we can say, well, what happens to f as we vary t? And that's the chain rule we talked about. That was from the previous part of the course. You build up your tree, which shows dependencies. And you say, well, if I want to know how f changes with respect to t, well, there's 2 ways. You go down through x, and that gives you your partial f, partial x, dx, dt. And you go down through y. And that gives you your partial f, partial y, dy, dt. You add them up, and that's how f changes with respect to t. Well, this can be written as a dot product, namely the gradient of f dot dr. And now we have our pieces in place. That says, oh, if you're integrating a gradient of f dot dr, then what you're really doing is you're integrating a derivative when you write everything in terms of t. Now, what's true? If you integrate a derivative of a function, what do you end up with? So I take a derivative and then I integrate. What happens? I can, for all intents and purposes, I'm back to the function. Now, of course, there's a pesky plus c, but we don't worry about that because we're amongst friends. So another way to say it is a really easy thing to integrate is a derivative. So we say, great. So now it's just what happens at f of x to t, y to t at alpha and beta. Well, when you plug in alpha, that's what happens at your start. When you plug in beta, that's what happens at your end. So you say, oh, all I have to do, find the potential function, and then say what happens to my potential function at my endpoints. I don't have to worry about the curve I took. Nowhere in this answer do I actually depend on the curve. So that again leads us to 2 strategies we've already mentioned. If we're trying to integrate along the curve gradient of f dot dr, one way we can do it is find the potential function and evaluate at the endpoints. Now, I say one way you can do it because you might remember sometimes integrating is hard. And you can know that something has an integral But that doesn't mean you can find it. So there is a second strategy, which we already mentioned, bring your own curve. Pick a better curve, but having the same endpoints. Now, one thing I didn't write down, but I should say it now. What we're saying here about line integrals is line integrals are easy for gradients. They're nice for gradients. And you might say, is there any other type of thing that I can integrate that has this beautiful property that really I don't care about the curve I took. The only thing I care about is that what happens at the endpoints. And the answer is no. So the only nice functions for line integrals are gradients. And if you think back to earlier in the week when we started talking about gradients, essentially we're saying those are things that have like a derivative. Or the gradient is a derivative of something. And so you can say, oh, there's essentially an antiderivative. So, all right. Maybe I should write this down while I pontificate. Line integrals are nice for gradients. And only for gradients. So, all right. So if it's not a gradient, you're out of luck. You definitely have to do something. Okay, any questions? All right, let's try this on 2 problems. We'll start with the one on the left. Find the integral along the curve y dx plus x dy where the curve C is shown. So this is the curve. I want to go from 0, 0 to 1, 1. I'm starting at 0, 0. I'm ending at 1, 1 because there's an arrow indicating direction. Okay, now, what aren't we going to do? We're not going to find that the way to write this line as a function of t. That's hopeless. Hopeless. Okay, so we're not doing that. So somehow, by giving us something that looks hopeless, they're trying to give us hope by saying, don't do that. So look for another way. All right, so we say, okay, there must be another way. Well, we look at this and start thinking, if this were a nice integral, life would be good. This is of the form integral along the curve of m dx plus n dy. What's our idea? Well, we want this m comma n. We want this to be the gradient of something. That's our goal. So if that were true, for us, that would say this y should look like an f sub x, and this x should look like an f sub y. So the question becomes, can we find an f so that if we look at the partial derivative of f with respect to x, we get y, and if we look at the partial derivative of f with respect to y, we get x. And at this point, it's okay to guess. Can anybody think of one? xy, okay. So we have a guess. And guessing is not a bad thing. A lot of math works best when you start with saying, look, I don't know what to do, let me guess. And then you find out what happens with your guess. And then you're right, or you get a better guess. So let's check. If I take the derivative of this function with respect to x, what do you get? Well, I'm asking the question. No, I won't do that to you. You're correct, it's y. What's the root of this function with respect to y? X. So it's like, this is a great guess. Okay. So now we're like, ha ha ha, moo, ha 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 ha. What do we care? Well, we say, look, this is equal to our potential function xy evaluated at our endpoints. Where's our start point? 0, 0. Our endpoint? 1, 1. So we plug in 1, 1. What do we get? 1, plug in 0, 0, what do we get? So our answer is 1. Not so bad. We're getting into like the find the antiderivative kind of mindset for today. So here's a different one. Find the integral along the curve of x squared dx plus y squared dy, where c traces out the curve x squared plus y squared squared equals 16x squared minus 16y squared. This is actually a fairly accurate picture. It looks kind of like an infinity symbol. And you start and end at the point 4, 0. All right. So what do we do? Well, we're probably going to have a really miserable time of trying to parameterize this curve. Even though we do have this as the functions of x and y, we do not want to try to solve for x and y as functions of t. At least not yet. We'd have to have a couple root beers in us before we wanted to start doing that. But again, let's sort of channel what's going on. We've got our x squared and our y squared. So we say, well, maybe, is it conservative? Well, okay. Can we find an f so that when we take our f sub x, we get x squared, and f sub y, we get y squared. Any thoughts? Does such a thing exist? Oh my gosh. 2 in a row?
1/3 x cubed plus 1/3 y cubed.
Let's check. We have another guess. F of xy is 1/3 x cubed plus 1/3 y cubed. Well, we can always check a guess. What's the derivative of 1/3 x cubed plus 1/3 y cubed with respect to x? X squared. Good. What's the derivative of 1/3 x cubed plus 1/3 y cubed with respect to y? Y squared. So, it is. Woohoo! Nice. All right, so what's our answer? Well, according to this, it's integral along the curve of x squared dx plus y squared dy is equal to this 1/3 x cubed plus 1/3 y cubed evaluated from, where do we start?
4, 0.
We start at 4, 0. Where do we end?
4, 0.
We end at 4, 0. So what's the answer? 0. Now, you should say, oh, it's 64 thirds subtract 64 thirds. Yes, which is still 0. Now, once you know it's conservative, there is another perspective, which is we can bring our own curve. So, we can say, okay, here's sort of a BYOC type idea. Can you think of another curve that starts and ends at 4, 0? And you're thinking too hard.
4, 0.
Just stay at 4, 0. The curve that just stays at the point 4, 0 starts at 4, 0 and ends at 4, 0. And what's the total as you move along the curve? 0, because you don't move. And so this is you're contracting down. You can pick a nice curve. Now, one of the things is that if you have a conservative function, right? That's one of these things is a conservative. If it's closed, the integral will always be 0. And it turns out that the only kind of functions where every closed integral, or every closed curve has an integral of 0 are conservative functions. So again, conservative functions are nice. Well, that's because conservative functions come from derivatives. All right. Well, that was pretty simplistic, but things are going to get more complicated quickly. So, some things. How do we know? How do we know that something's conservative? Well, there's a test. And so if we're given a function, we're like, well, gosh, golly and gee, start channeling our inner 1950s sitcom character, what do? Well, we say, let's look at our function. If it's supposed to be conservative, the first piece is supposed to be the derivative with respect to x of the potential. And the second is supposed to be the derivative of y of the potential. Now, we say, oh, notice if you take the derivative of the first piece with respect to y, and you compare it to the derivative of the second piece with respect to x, you get what are the mixed partials, fxy or fyx. Those should be equal. So, if you're conservative, these partial derivatives have to match. It turns out that's sufficient. As long as those partial derivatives match, you are conservative. So that's a test. So even if you can't find the potential function, you can at least verify it's a conservative function. And that's how you can say, bring my own curve. Now there's a similar test for 3D, but instead of listing it out, we go back to something we mentioned at the end of class a few times ago, which is if you take the curl of the gradient, you'll get 0. And that turns out the only way you get the curl of something equaling 0 is if you start with a gradient of something. So your test is take the curl. If you get 0 out, you're good. And I wrote down what the gradient cross f is. And I just want to point out this n sub x minus m sub y, if you set that equal to 0, it's the same thing as saying m sub y equals n sub x. Okay, so that's testing, but how do you find the potential function? And I say, I used to make things overly complicated. As I've gotten older, I realized there are simpler ways to do it. So this is my current strategy, and I think it's very easy and straightforward to apply. So if we're finding a potential function, we say, what do we have? We have a collection of partial derivatives of our function. So, idea. If I integrate my derivatives, what should I get back? The function. So let's do that. We integrate all the partial derivatives. So that's the first step. Integrate the partial derivatives. And include appropriate constants. I'll explain what I mean by that in a moment. After you do that, you say, okay, let me look at the things I have as my answer. I have to check for consistency. So what I mean by checking for consistency is if something involves more than one variable, it has to show up in more than one place. It has to show up, let's say it's an expression that involves both x and y. It has to show up in the part where I integrate with respect to x, and it has to show up in the part I integrate with respect to y, and they have to match. That's the consistency check. If there's not consistency, there's problems. And essentially that's a different way to test for a conservative. If you fail the consistency, you're not conservative. But if you are consistent, you just combine, don't double dip. In other words, don't overdo it. Let's just go through and do an example. There's space here. Find the potential function for, we have 4x cubed plus 9x squared y squared, 6x cubed y plus 6y to the fifth. Some of you probably can look at this and say, I figured it out. But let's pretend like we haven't gotten to that stage yet. So here's the idea. This first piece is f sub x. And this second piece is f sub y. If it's conservative, that's what we have. Our goal is what's f. So we start step 1. We say, if I want f, I just integrate f sub x dx. And that should give me my f. Well, that becomes the integral of 4x cubed plus 9x squared y squared dx. So we're integrating with respect to x. How do we treat our y's? Constants. So these are indefinite integrals. These are antiderivatives. What do we get? X to the fourth, 3x cubed, y squared, plus c, good. And then I'm somehow keeping my pen near here as though there's more to write down. Oh, are you asking me why do I put my pen here as if there's more to write down? Oh, you have turned the table, sir. Thank you. Thank you. Or have you meant to say, oh, I meant the variable y. Oh, you meant the variable y. You could have turned the tables. C of y. Why is there a c of y? Well, it's a constant with regards to x. Right? Because we integrate with respect to x. So anything which is constant with respect to x. So that's anything not involving x. So it can be an expression that includes y. All right. We are going to do the same thing again. We have to do it for all of the pieces. Integral f sub y dy. So, if this is derivative with respect to y, integrate with respect to y, we should get our function back. So we get 6x cubed y plus 6y to the fifth dy equals. So we're integrating with respect to y. What do we do with these x's? Treat them like constants. So what do we get? 3x cubed y squared. What else do we get? Y to the 6 and? Well, plus, we already used c, moving our way up through the alphabet. Something that's constant with respect to y. So that can be anything which depends on x. Okay, so now we check for consistency. Okay, is there anything which involves multiple variables in our answers? There's the 3x cubed y squared. Now, because it involves both x and y, I have to check, does it show up in both x and y exactly the same? And does it match? Yes, that's the consistency check. If it involves both x and y, it has to be in both places in the same way. Okay. Now, you might say, well, wait, this x to the fourth, where is it down here? It's actually, yes, in the d of x term. And on the other hand, this y to the 6, where is it upstairs? It's in the c of y. That's why you have to do each piece, because you're going to put it all together. So we checked for consistency. The last thing is to write our answer down. So our potential function is, we just pick the pieces. So we have, we'll put the common part, 3x cubed y squared, the x to the fourth, the y to the 6. The don't double dip says don't add this twice. So you don't want a 3x cubed y squared plus another 3x cubed y squared. You just need it once, because it'll handle both of them simultaneously. And that's the potential. All right, how are we doing? Okay, good. Should we try another one? Yes. Let's go up a dimension. What did you expect me to go down? Go down a dimension? Wow, that's so last year. We're multivariable people now. All right. Find the potential function for this. Do we have a potential function we can put down here in the corner? Do we have pieces of a potential function we can put down in the corner? Oh, apparently our potential function will include an x, y, z. I heard. Any other pieces that we might have? A what? E to the x cosine y. Okay. Anything else? And e to the y z. Yep, that'll be there. Anything else? Arctangent x. Gotta love that. Anything else? Tangent z. Anything else? A y cubed. Anything else? And the answer is, well, it depends what you want. Okay, let's go through it quickly. And we'll come back and say, is there anything else at the end? And someone will say, oh, I know what Steve went to say. Okay, so we have our derivative with respect to x, our derivative with respect to y, our derivative with respect to z. So we're going to integrate them all. So if we integrate our integral with respect to x dx, well, I'll just integrate here. I'm just screening it off. You get e to the x cosine y, arctangent x, and xyz, plus a function of what? Y and z. Anything that doesn't depend on x. Okay, do the same thing with the next two slots. Take the integral with respect to y dy. So we come here integrating with respect to y. It'll be an xyz, a y cubed. Integral of minus sign is positive cosine. So e to the x cosine y. And here, integral of z e to the yz with respect to y is e to the yz. Plus a constant with respect to x and z. Do this one last time. Once more to the breach, dear friends. Integrating with respect to z, we get xyz. Integral of y e to the yz with respect to z is e to the yz. Integral of secant squared z with respect to z is tangent of z. Plus some function which depends on just x, y. So anything that only depends on x and y. So we start checking for consistency checks. I see an e to the x cosine y in the x part. So what else do I need? I need an e to the x cosine y in the y part. So that's a consistent one. So that's good. Arctangent x is fine as is, because it only depends on one variable. So I don't have to check for multiple locations. How about the xyz? Well, where do I need to check for? Yeah, it's got to show up in all of them. Well, good news, it's here in y, and it's also here in z. So it's consistent throughout. Also, we have to check e to the yz. Well, that depends on y and z. It shows up in y, and it shows up in z. So there's consistency. And then you have your last three parts. Again, you don't have to check for consistency, but they're all there. There's the arctangent of x, there's the y cubed, and there's the tangent of z. So it passes the consistency check, and now you put it together. So you have your e to the x cosine y, you have your xyz, you have your e to the yz, you have arctangent of x, you have tangent of z, and you have y cubed. So, is this the potential function? No. Ooh, Steve phrased it a weird way. Why not? What's missing? What's the change? So the thing is, antiderivatives are not unique. So it is correct to say this is a potential function. So really we should talk about finding a potential function. If you wanted to get all potential functions, you'd add on a constant. But when we find potential functions, we're actually going to evaluate, so you don't have to worry about the plus c. And we'll stop here. And we'll pick up again next time.